A very important topic that we are going to talk about now is the drawback of the Bohr-Sommerfeld model. We all know that Bohr-Sommerfeld model did explain a lot of properties of the atom, but there are certain drawbacks, or we can say that there are certain properties which it could not explain. Let's just have a look into a few of these important examples. So it did give a very good theoretical, background of the fine structure. But then it predicted the fine structure, but then the spectral lines of hydrogen, but it could not predict the correct number of observed fine structure of these lines. So there was this idea that there will be some kind of fine structure, but the exact number of lines could not be predicted. As you all know that we are talking about the hydrogen spectrum. These means that we are talking about these lines, which we are actually, talking about Lyman, and you might have studied in your lower classes like Balmer, Preston, Brackett, and P5, right? So this is Lyman, Balmer, Preston, Brackett, and P5. Now these lines, the fine structure could not be explained clearly by the Bohr-Sommerfeld model, and that is actually a very important drawback. It also could not explain the distribution and arrangement of electrons in the atom. There is this concept of orbit and orbital. According to Bohr, the electrons are revolving around the orbit, but the real picture is more or less quantum mechanical in nature. That means that the electron can be anywhere in the sphere in the first shell, but it's not that it will be actually moving around only around this orbital. So that was actually the second drawback. The third drawback was Sommerfeld model was unable to explain the spectra of alkali metals such as sodium, potassium, etc. So I'm going to talk about the spectra of sodium atom, that there are two fine lines which are actually being observed. But let me tell you, spectra is a very important part where we are able to know the unknown material by looking into its spectra. It also could not explain the Zeeman effect and Stark effect, although we are going to discuss about Zeeman effect and Stark effect in our upcoming classes. But let me tell you that if there is a transition of an atom from the upper energy level to the lower energy level, we are going to get some emission of radiation or photons. But if we are putting this entire setup in a magnetic field which is relatively weak compared to the internal magnetic field of the atom, the chances are that we are going to see that this line will actually split, and we are going to get some more lines coming out of it, or some more radiations coming out of it. So instead of one, there will be three radiations when we are actually putting it in a magnetic field. Now that's an example of a normal Zeeman effect. If there are more lines, it can be an anomalous Zeeman effect. So this again could not be explained by the Bohr-Sommerfeld model. Stark effect, something similar. We are not placing it in a magnetic field, rather we are placing it in an electric field, and we are seeing a similar observation. So these could not be explained by the Bohr-Sommerfeld model. And finally, although it can talk about the Lyman, Balmer, Bastian, Brackett bond lines, and it can talk about the fine structure of the hydrogen atom, it could not predict the number of lines, and at the same time, it could not also tell you the intensity of these spectral lines. So what's the solution to this? Well, then a new model was actually established. A number of scientists have contributed to that, including Bohr and Sommerfeld, and which came up with the vector atom model. If you refer to the first lecture, we have discussed about the vector atom model. But there are two main features of the vector atom model, and if there is a question on these features, would be a very important point to write down. So we have something which we call as the spinning electron, and the second feature is the space quantization. Now what do I mean by spinning electron? So until Bohr time, and after that when the fine structure of spectral line was explained, it was observed that the electron will actually move around the nuclei, but then the electron will also have a spin of its own, which might be plus half or it might be minus half, depending on whether it's up spin or a down spin, or a spin in the clockwise direction or in the anti-clockwise direction. So this is the idea of spinning electron. And because of these spinning electrons, the electrons will actually have some kind of additional energy. Well, that also explains something which we call as the doublet in case of the yellow sodium light. Now, if you have not come across this, in labs usually to do any kind of a lot of optic experiment, there are sodium lamps which are being used, and if that's a very good source of almost a monochromatic source of light. Well, the sodium lamp or the sodium light has got two wavelengths attached to it. One is 5890 angstrom and the other line is 5896 angstrom. Now you see these two values are very close to each other, and all of us know that 1 angstrom is 10 to the power minus 10 meter. If you look into the range, these are very close to each other, and that means these lines are separated by a distance of 6 angstrom. This gives rise to something which we call as doublet. That means there are two wavelengths which is coming out of the sodium lamp, but it is very close, so it's nearly monochromatic. So even if there is not a perfect monochromatic source, sodium lamp can be used because it's more affordable for the normal lamp. So this actually is a consequence of the spinning electron. Similarly, we have it for mercury, which is called the triplets mercury. Okay. But we are not going to explain that right now, but this is an important concept of the spinning electron. So if the electron spins, the spin quantum number would be this, okay, and it will have a magnetic spin quantum number associated with it as well. Okay, so if you want to find out the magnitude of this spin, you can basically just write it down as the spin of one electron into s plus 1 into h cross. Now this is something which I have already discussed in lecture 1, so you can go and refer back to that. So if you want to write down a note on spinning electron, you should obviously talk about the half spin, minus half spin, up spin and down spin, and also about the sodium doublet line. Next, the second feature, which is very important for the vector atom model, is the idea of space quantization. Now when we talk about the Bohr model, we have the electron around the nuclei, and it is basically a two-dimensional picture, which is actually not true. The electron revolving around the nuclei will basically have three-dimensional image. That means it will basically have two quantum numbers, which is already there is an established idea that there will be two quantum numbers from the Bohr model, but then there will be a third quantum number because it's a three-dimensional image. So there are altogether three quantum numbers. The quantum numbers that we already have talked about are L, L, ML, and so, right? So these things will actually comprise, and this idea comes from the idea of the vector atom model. Space quantization, as you know, the space or the rotation that it will basically have, or the orientation that the atom will have, will also be fixed. It's not that it will have an orientation in any direction. That means even the rotational direction, or if we are applying an external magnetic field, the resultant angular momentum will start revolving around, let's say this is your angular momentum quantum number, this is your space momentum quantum number, or the spin momentum quantum number, and then this would be the resultant J, and the resultant J will be spinning around the magnetic field. Now this motion around the external magnetic field will also be fixed. That means this will be also quantized. It's not that it's going to revolve or rotate in any direction. So that's why we use the term quantization. So this is the idea of space quantization. Probably this might be a 2 marks question